How optical fiber isolated probe wins over differential probe. Both MIXIG optical fiber isolated probe and high voltage differential probe can be used for floating tests. But what is the difference between the two probes? Today we'll compare from multiple aspects: bandwidth, common mode voltage, differential mode voltage, signal to noise ratio, CMRR, bandwidth flatness, and safety of test. So to help choose the right probe in different scenarios. Of course, you don't need to make choice. When you got sufficient budget, just choose the optical isolated probe from MIXIG. Now, let's start with bandwidth. MIXIG optical fiber isolated probe has bandwidth up to 1 GHz, while the high voltage differential probes are usually come with 100 MHz. 200 MHz ones are quite few. In fact, when the bandwidth of high voltage differential probe is higher than 50 MHz, the higher bandwidth part basically has no accuracy. Why? Let's test a signal first. This is an oscilloscope calibrator. The output signal has higher accuracy. Can output 150 ps fast edge signal, which is really good. Oscilloscope's accuracy is dependent on such equipment. Let's input the fast edge signal directly to the oscilloscope. Save the waveform for afterwards comparison. Here is a differential probe with 200 MHz bandwidth. Let's input a fast edge signal to the differential probe. We can see that the signal has big oscillation. It means the output amplitude of the differential probe will be different at different frequencies. Let's verify this with a sine wave. Input a 3V, 10 kHz sine wave. Sweep from low frequency to high frequency. Check the differential probe's amplitude. We can see, as the signal frequency changes, the output amplitude of the differential probe fluctuates, with no accuracy. Therefore, no matter how high the differential probe's bandwidth is, it is useless to measure. This is a 500 MHz MIXIG optical fiber isolated probe. Input the same fast edge signal. We can see the waveform is so smooth. Then same as the differential probe. Input a 3V, 10 kHz sine wave. Sweep from low to high frequency. Check the signal amplitude again. Even at 300 MHz bandwidth, the optically isolated probe still has 1.5% accuracy. At 500 MHz, the attenuation is less than -3 dB, reach the nominal bandwidth. Next, let's compare the common mode voltage. High-voltage differential probes use large-value resistors to limit the current. To convert high voltage to low voltage, the measured differential mode voltage is the highest common mode voltage. For instance, the max measurement voltage of the differential probe is 1500 volts. Then the highest common mode voltage is also 1500 volts. Common mode signals above this voltage cannot be rejected. That could endanger equipment and personal safety. MIXIG isolated probe adopts fiber optic isolation technology. Transmits the signal from end to end via a fiber cable. Without electrical signal. Achieve true electrical isolation. Able to conduct floating measurement under high common mode voltage. Although the nominal common mode voltage is 60 kV, you don't actually have to worry much, as the optical fiber isolated probe can test any high voltage as long as the environment allowed. Now is differential mode voltage. High voltage differential probe can only test fixed differential mode voltage, while the MIXIG optical fiber isolated probe can measure different voltage by using different attenuator tips, such as 10, 1, 20, 1, all the way to 2001. So what about the differential probe? It has two voltage ranges, 150 volts and 1500 volts. Simple to understand. When we switch the range to 1500 V, connect the probe with a signal of 1500 volts. The signal output from the probe to the oscilloscope is a full-scale output. Any added voltage will be over range. What if we want to measure a small voltage? Switch the range to 150 volts. The 150 volt input voltage can be output in full scale. The smaller signal is, the smaller amplitude will output. But does that mean we can measure any signal smaller than 150 volt? Not exactly. There's problem of SNR, or the signal-to-noise ratio. Connect differential probe to channel 1, MIXIG optical fiber isolated probe to channel 2. Both input a 1V sine wave. We can see the optical fiber isolated probe flexibly change the attenuation ratio to adapt to different voltages. The probe maintains the maximum output from small signal to large signal, which greatly improve the SNR, and the signal looks much cleaner. Now let's compare the common mode rejection ratio, or CMRR. Connect the positive and negative input end of both differential probe and optical isolated probe to the center point of the half-bridge device. Now the inputs of both probes are short-circuited. We can see an oscillating signal on differential probe on channel 1. That means the differential probe has poor common mode rejection ability, not able to suppress the common mode interference. Meanwhile on channel 2, the MIXIG optical isolated probe shows a very straight line. Common mode interference has been perfectly rejected. Now connect both probes to the high side of VGS at the same time. We can see due to low CMRR of the differential probe, the high-frequency common mode interference is not rejected, while the MIXIG optical fiber isolated probe completely immune to such interferences. Lastly, let's compare the safety when testing gallium nitride. Engineers who familiar with GaN power supplies have more experiences. Gallium nitride circuit is easy to blow up during test, especially when used a high-voltage differential probe or a passive probe. Now we can choose optical fiber isolated probe to test GaN. It's very safe. No explosion danger. For more specific principles, you can search related video on MIXIG YouTube channel. Above all, we can concluded that MIXIG optical fiber isolated probe can fully replace the differential probe.